Okay, I do want to highlight, especially part D from a couple of these problems, since they're just a bit more challenging and also ones that feels different than the ones that we've seen. So if you can turn to page 5, I do want to kind of go through part D from page 5. So. Okay, so page 5. Here's the big picture. So part D says, suppose f prime of 5 is equal to 3, and f double prime of x is less than 0. So what that tells us is that the slope of the graph at 5 is 3, and its second derivative means what? Concavity, right? So the graph is concave down. So what happens is, if I have a slope that is positive, but concave down, what that means is that if I create a tangent line, I can create a tangent line just by getting order pair and slope and build that tangent line, right? This tangent line, where is this going to be in relation to the curve? Above or below? Above, right? So that means any point that I use to approximate, or any point that I find on that line, is going to be sitting higher than the curve. It's going to over approximate the curve, and that's what that's what they're trying to have us do. Is that if I can prove that this is a certain value, then I know that the true value on the graph is going to definitely be below it, right? Because the graph is concave down. Okay. What if the graph was concave up? Then any tangent line is going to do what? Over or under approximate? Under. Any point that I find on this line is going to sit comfortably below the curve. Okay. So depending on how the graph is, whether it's concave down or concave up, your tangent line is either going to sit above or below. Now, the second part is talking about secant line. So secant line, let's say we have the same graph as before. A secant line is where it goes through a line that goes through 2 points on the curve. So I can build a secant line if I can take 2 points, find the slope between those 2 points, take either order pair and do point slope form and build this line. Now, where is this line in relation to the curve? Any value that I find on this line is going to do what? If I find a point on this line, is it going to sit above or below the curve? Below, right? So it's going to be the opposite, right? So if my graph is concave down, a tangent line is going to sit above the curve, but a secant line is going to sit below the curve. So tangent line is going to over approximate a point on the curve. A secant line is going to under approximate the point on the curve. And likewise, if I have a graph that's concave up, then any secant line is going to do what? Over or under approximate the curve. It will sit above or below the curve. Above, so it's going to over approximate. Meanwhile, the tangent line will under approximate. But we're in this scenario here where we know the tangent line is going to over approximate, our secant line is going to under approximate. So that's what the process that I went through on my key here. Since the graph is concave down, we know the tangent line is going to sit above the curve. So to build the tangent line, we just take the order pair, we take the slope, do point slope form, plug in 7. And if I plug in 7, I get 4. So if I know that a point on this curve is sitting at a y value of 4, if I know the point on the line has a y value of 4, I know that the point on the curve must be lower than 4 because I know the tangent line is going to sit comfortably above the curve. So that's the justification that we're able to make. Show that f of 7 is less than or equal to 4 because the tangent line is at 4, so the point on the curve is definitely less than 4. And then to find the secant line, which is this line right here, we just take the order pair that is provided on the table, and we build that slope. So change in y over change in x, we find that slope, which is 5/3. So we can take either point and do point slope form. And now that we build the tangent line, the secant line equation, we plug in 7 and we actually get 4/3. So if this point on the line is 4/3, then we know the actual point on the curve is going to be greater than 4/3. Okay, I also want to go over number 6, part D as well. Part D says the light is directly above the western end of the track, then rides so that at time t, the distance L of t satisfies L of t squared equals 12 squared plus b over t squared. At what rate is the distance between bend and light changing? So we're looking for L prime. So to do L prime, we have to find the derivative. To find the derivative, we have to recognize, oh, this is chain rule here. We got an outside and inside portion. So we do 2 bracket to the first power times the inside derivative. So L becomes L prime. And then 12 squared goes to 0. B of t squared becomes 2. B of t to the first power times b prime. And then we're just plugging in the values that's given to us in the table to find our L prime 40. Okay, 7 and 8 are both particle motion problems. So let me skip those for now. That'll be part of your homework. I do want to go over 9 and 10 with you. 9 and 10, these are the rate in, rate out problems that won't be on the quiz, but I want to make sure that we still remember how to do these types of problems. So let's go to page 9. Practice related rates. This is rate in, rate out. Yeah, so similar to the problem that we did with people entering the amusement park, people exiting the amusement park. So new topic. This was the last thing. That's right. Yeah, this really was the last thing that I introduced to you. I mean, we know what integral means, but we haven't quite seen it. But yeah, this is really the last thing. So really, we're all pretty much in review mode. Okay, so here's page 9. A water tank at Camp Newton holds 1,200 gallons of water at time t equals 0. So we have water in the tank to begin with when t equals 0. During the time interval, water is pumped into the tank at a rate of W of t. So we have some rate at which water is coming in, gallons per hour. During the same time, water is also being removed from the tank. So water is coming in, and water is also being removed, okay, at a certain rate. They're both in gallons per hour. Part A, is the amount of water increasing at time t equals 15? Why or why not? So what we can do is we can figure out which one is pulling or which one has higher rates, right? Is there more water coming in or is there more water leaving, right? If there's more water coming in, then we know that the amount of water is going to be rising. If there's more water leaving, then we can just, we know that the water is going to be falling. So we can just plug in 15 in for both of these and see which one has a higher value, right? If R of t has higher value, then we know more water is coming out. If W of 15 is higher value, then we know more water is going to come in. So we'll do W of 15. And we'll find R of 15. In fact, we just subtracted, right? If W of 15 minus R of 15 is a positive number, that means more water is coming in. If R of 15 is more than W of 15, we're going to get a negative number. If we get a negative number, we know that there's water being pulled, more water coming out than going in. So we know the water level should be dropping. So let's go ahead and just put them into Y1 and Y2, since we may have to be calling them out anyways. So 95, we're going to use what variable here? X, yeah. Now, the way that you're going to enter this in the calculator, we can't do that square notation the way that we see it. So where do we have to put that square in the calculator? Outside, yeah. So you got to write it this way. You got to say 95 root x, and you got to do big parentheses, sine of parentheses x over 6, parentheses squared. Okay. I wish that the calculator had a way to do this, but we have to understand that there's no notation for us to put that squared there. We have to put it in this form. Okay. Same thing here, 27 parentheses sine of x over 3, close parentheses squared. If you want to do the math print for the fraction, you can do alpha y equals. Okay, so I have y1 and y2 inserted in, so I can just call these. I don't have to enter them again. I just call y1 and y2. So I'm going to go back to my home screen, my main screen, second mode. And now I'll do alpha trace. I'm going to call y1. And I'm just going to insert in 15. I'm going to go minus alpha trace y2. 15. So I'm just basically doing W of 15 minus R of 15. Let's see which one. So we get a positive number. What does that mean? Oops, sorry. I messed up. Oops, I entered in sine of x over 6 for y2, but it should be sine of x over 3. Let me try again. There we go. Negative 121. What does that mean? Negative 121.
Decreasing.
Decreasing, yeah. So that means my R of t is going to be a larger value than W of t. That's why I'm getting that negative number. So we know that the amount of water is decreasing at this rate. It's decreasing by 121 gallons per hour.
That's saying decreasing, just say it's not decreasing.
Yeah, either way, it's asking whether it is increasing. So we can say it's decreasing, or we can say it's not increasing. I think they both answer the question.
You didn't call it the word take over. Nothing was on the explain stuff.
Yeah, yeah. But in this case, I think both will be acceptable. Part B, to the nearest whole number, how much water is in the tank at t equals 18? So we talked about how this is rate in, rate out formula, where sometimes there's three components we got to consider. We got to consider how much is there to begin with, how much has been added, and how much has been removed. So if we take all those three things into consideration, then we can figure out how much is left after all three things have been accounted for. So let's create that formula. So here's we can say the amount of water at any moment in time is equal to the initial amount plus the amount added minus the amount removed. So that's a good formula to know, especially when you recognize that it's a rate in, rate out problem. Or it could be, this can apply in from that context of number of people entering and exiting amusement park, right? The number of people in the park is how many is there to begin with, how many have entered the park, and then subtract the number that's left the park. So it can apply in all those situations. So let's create a formula that we can use. So we'll do this. We'll say A of t is equal to, and I'm leaving them as variables so that we can adjust to any moment in time that we want to use later. But we know initial amount, A of 0, plus the amount added. So we know W is rate. So if we accumulate that rate using the interval, we're going to get that gallons per hour to be in terms of gallons. So we know this is going to give us something in terms of gallons. We're leaving that upper bound T as a variable because we want to be able to have the flexibility to say, okay, how much water is in the tank 5 hours in, 10 hours in, 12 hours in. We don't want to, it's nice to just have a formula that we can constantly go back and reuse. And whatever variable we put up here, we want to go ahead and make sure that this is a different variable. So W of X, same thing as W of T. We just left this in terms of X so that T will get inserted for X later on. And then since R of T is amount removed, or the rate at which water is being removed, we can say the depth integral from 0 to T of R of X dx. Okay, so that's the formula. And then for part B, it's saying to the nearest whole number, how much water is in the tank at 18 hours? So we just do what? Replace every T with what? 18, and just make the calculator do all the work for us. Okay, so here we can do math 9, 0 to 18, and call Y1 minus math 9 from 0 to 18, and then call Y2, since we have Y1 holding W and we have Y2 holding R. And all this goes in our calculator, and we should get 1310 gallons. Okay, let's look at part C. Part C says, at what time between 0 and 18 is the amount of water in the tank at an absolute minimum? So what is that a hint to use? Yeah, extreme value theorem. So we got to find endpoints and critical points, right? So we know we're going to test 0. We got to find the amount of 0. That's easy. We already know that. We got to find the amount at 18, which you already know. And now we have to find critical points is where our critical point is. So for part C here, we know we have to apply EVT. We know we're going to test endpoints and critical points. And critical points is basically wherever our A prime of t is equal to 0, right? Now we have A of t, so let's build the derivative here. So if I want to build a derivative, that means we're going to make every term go through a derivative process. What's A of 0 going to turn into? This is just 1200, right? 1200 will just go to a what? Derivative, 0. And then if I want to find the derivative of this, it's going to happen if I have a derivative on top of an integral of a function. Cancel out, I'm just left with W of, yeah, good, W of t. And then minus, this is what? R of t. So we just want to figure out when is W of t minus R of t equal to 0. So the easiest way I think to do this is let's just graph this and look for the what? Yeah, look for the, yeah, you can either graph it, look for the intersection, but I prefer graphing this and look for the x-intercept. That way you don't have to search all over, you know, if it's 95 and 275, who knows, you know, how far you have to move up on the y-axis in order to get these two graphs to intersect. I find it easier to just search along the x-axis because we only have to search along between 0 and 18, right? It's gotta be a t-value between 0 and 18. So I'm going to go to my y equals, and I'm just going to do y1 minus y2. That's basically my w minus r. So I'll do y1 minus y2. And I don't want to have to look at both the w and the r equation all mixed in with the graph that I want to see. So I'm going to actually go to the equal signs for y1 and y2. I'm going to hit enter on the equal sign so that they will not show up. So if I unhighlight the equal sign, that means it's still in the calculator, but it's not going to show up on the graph for me. So y1 minus y2. I'm going to adjust my window. I know that I'm looking for an x-intercept between 0 and 18. And I see that my equations are in the hundreds, right? I got that 95 root t, the 275. So I'm going to say negative 100 to 100, just so that I'm not zoomed in too far. And I can always go back and adjust these numbers if it doesn't look right. Right, so 0 to 18 for x min, x max, negative 100 to 100 for y min, y max. I'll hit graph, see what that looks like. Okay, that's pretty good, right? We can just do second trace 0 to find that x-intercept. This is probably more than 18, so I think this is all we need. Okay, I get 6.49. Oh, actually, there's one more. Yeah, let's see if this is, yeah, because I had 18 all the way up here, so it looks like this is going to be within that range as well. So I'll do second trace 0 again. So the left and to the right of the x-intercept. I'll hit enter. 12.974. So we know we got to test 4 points, right? We got to figure out the amount of water at 0, the amount of water at 18. Actually, we already have those. We just have to find the amount of water at 12.9 and the amount of water at 6.4. So we'll just take all those and plug them back into AFT equation. And then we'll compare the y values. Well, the nice thing is we already have 0 and 18. We know that 0 is 1200. We know 18 is 1310. So we just have to use the same formula. Just replace the upper bound with 6.495 to figure out how much water has entered the tank in the 6 hours, how much has been removed, and we should get 525. And we'll do 12.975 as well. Do 1200 integral from 0 to 12.975 for y1 minus 0 to 12.975 for y2. And now you're comparing these numbers here. You're looking for the lowest. So the absolute minimum amount in the tank is between the 18-hour period is going to be 525 gallons. So this is the pattern for a lot of these rate in, rate out problems. You'll use the amount equals initial plus amount added minus removed. Then they're going to ask you for max and min. So you build your A prime, and then you graph, look for the x-intercepts, consider those x-intercepts as part of your critical points and your test endpoint and critical point, plug them back into your AFT equation. Right, so that's the pattern that we've been seeing with these rate in, rate out problems. In terms of how they're designed. Okay, part D. When T is greater than 18, no water is pumped into the tank. So only water is getting removed. So until the tank becomes empty. Let K be the time at which the tank becomes empty, right? But do not solve an equation involving integral notation that can be used to find the value of K. So we know that we're just going to be draining water out of the tank, but however much water is in the tank to begin with at 18 hours, will just continue to decrease, right? Because there's no more water that's going to be added. So we know that there's going to be 1,310 gallons of water in the tank. So we can just rely on the integral of R of T equation and say that, you know, from 18 to K, however long it takes for this to equal 1310, right? So we'll need to drain from 18 hours until however long until this can reach 1310, because once we do that, then we know that all the water in the tank is going to be removed from the tank because we have 1310 gallons to remove from 18 hours on.
That's it.
That's it. That's it. Yeah. Okay. Let's look at number 10. Okay, so there is no snow on Janet's driveway when snow begins to fall at midnight. But from midnight to 9 a.m., snow accumulates on the driveway at a rate modeled by F of T cubic feet per hour. So this is a rate, the rate at which snow is falling, where T is measured in hours since midnight. Janet starts removing snow at 6 a.m. The rate in cubic feet at which Janet removes snow from the driveway after midnight is modeled by. So from midnight until 6 a.m., she's in the house. She hasn't come out yet, so she hasn't shoveled any snow off the driveway. But then from 6 to 7, she is making progress at 125 cubic feet per hour. But then from 7 to 9, for the next 2 hours after that, she slows down. It's only 108. She's still making progress, but it's less than the first hour. So 108 cubic feet per hour for the next 2 hours. Right, so she's out there for 3 hours, 125 cubic feet per hour, and 108 cubic feet per hour for 2 hours. So we actually can find out exactly how much snow she's shoveled, because we can take this. This is for 1 hour. This is for 2 hours. So it'll be 125 plus 216. That's exactly how much snow she has removed. Okay, so part A. How much snow has accumulated on the driveway? So the only thing we need for part A is what? Which information? Yeah, just F of T, right? We don't need G of T, because G of T is removing the snow. We just want to know how much snow has been accumulated. So can we just plug 6 in for T, or how do we find the accumulation of snow by 6 a.m.? Take the what? We need to do, how would you set that up for part A? Yeah, take the integral, right? So we'll do integral from 0 to 6. 0 represents 12 a.m. So we know that this is per hour. So we want to accumulate that over a 6-hour period. So we'll say the integral from 0 to 6. Put that in our calculator. Now, the function started off as cubic feet per hour, but if we're accumulating that rate, it's going to turn into cubic feet. Part B, find the rate of change of the volume of snow on the driveway at 8 a.m. So we're going to be dealing with rate of change, so we can leave it in terms of F and G. There's no need to adjust it, because this is already in cubic feet per hour. This is also cubic feet per hour. So we just have to compare at 8 a.m. You know, which one is doing that at a faster rate? Is there more snow coming down at 8 a.m. or is there more snow being shoveled off? Because if there's more snow that's being shoveled off at 8 a.m., then we know that that means the rate of change is going to be decreasing, right? So we can just do F of T minus G of T, right? If F of T is higher, then there's more snow being added. If G of T is higher, then we should get a negative number, which means that more snow is being removed. So we'll do F of 8 minus G of 8. So F of 8 is just plugging 8 into the function F of T. Then what's Janet's rate at 8 a.m.? Just 108. Yep. So we just subtract those two numbers. And hopefully it's a negative number. That means Janet is making progress and that more snow is actually coming off than being added. So yes, there's progress being made by Janet, right? She can see that at 8 a.m., the snow on the ground is being removed at 60 cubic feet per hour.
How come on the first one you have to do like the interval,
Mhm.
and then this one you don't? Like, how do you know?
How do we know, right? Okay, so here it says how many cubic feet of snow. So we're looking for the amount of snow. So if we're doing an amount of snow and we're sitting at a rate, we got to convert that rate to a different unit. So anytime you want to convert to a different unit, there's going to be some calculus involved. But for part B, it says find the rate of change of the snow volume. So the rate of change is the cubic feet per hour. It is in the proper form. It is in the proper unit. So if we're already sitting in the unit that we need to, there's no need to do anything with calculus. Yeah. Okay, part C. Let H represent the total amount of snow removed from the driveway. So we're going to be using this formula as well. Total amount equals initial plus amount removed, but it's a little bit different because we're maybe not used to dealing with piecewise functions and how piecewise functions work. So, but yeah, I do want to walk us through this problem. But it may take longer than the amount of time that we have remaining. So I want you guys to try it though. See if you can work through this problem. But I will walk through the rest of this problem with you. And the homework is pages 7 through 10 tonight. All right. All right, come get your phones.
On the right track, but it's a little bit more involved in that, so let me go through it.
Cool.
I don't know what we're doing. It's really. I'm also going to 48. Yeah, like, my teacher, I mean, so that divide us, they are more under. Thank you. It's not like there's one of them that good. Thank you. Good. I was about to say we were going to say. If you were UGA or UGA, this is another one basically.